Steinhauer here. Welcome back. We've come to the moment in the class that many of you have been waiting for. We get to talk about black holes and curved spacetime. We're up to chapter 24 in our astronomy textbook. So let's start with some background that we need before we can understand what black holes are and how they work and what they're like. So the story, of course, begins with this very famous person, Albert Einstein, who was already very famous by 1916, but in 1916 published the papers that unlocked the why of gravity. So you might remember we've already talked about Isaac Newton, and Isaac Newton unlocked the how of gravity. Remember Newton's formula, force of gravitation is equal to big G times the product of the masses divided by the distance between them squared. And this, even up until 1916, had worked fine to explain every single physics experiment that had ever been done at the time. So the problem was not that Newton's law of gravity wasn't working. It was that Einstein was bothered by a particular aspect of it. And it's the same aspect actually that Newton himself was bothered by, which is how and why. Why is it that the moon feels a force from the earth? They're not connected in any way. They're not touching. What is it about the earth that causes the moon to orbit around it? What is it about the earth that causes us to fall down towards it? What is it about the sun that keeps the earth in orbit around it? That was the question that was bugging at the back of Einstein's mind. And in 1916, he cracked the nut. He figured it out. So let's think about where he started from. His starting point for his theory of general relativity, which is the one that cracks the gravitational nut, is the principle of equivalence. And the principle of equivalence says this: if you have two observers, one of whom is on the Earth, let's say, and experiencing gravity as normal, and you have another who is in a rocket ship, and that rocket ship is accelerating, there is no experiment that an observer can do to distinguish between those two events. Let's try to unpack that a little bit. We've got pictures of two Albert Einsteins, one of them standing on the Earth and the other one standing on a rocket, which is accelerating in this direction. So this Albert Einstein on the left experiences the world as we experience it. This person feels weight, feels pressed against the earth. If this person were standing on a scale, it would register some force. If Albert Einstein releases a ball, obviously that ball accelerates down and hits the earth. Let's think about Albert Einstein on the rocket. The same thing happens. Because the rocket is accelerating in this direction, Albert Einstein feels pressed to the floor. If you put a scale down there, it will read a non-zero number. He will have a weight. If Albert Einstein takes a ball and drops it, it will go straight down. And so this is the equivalence principle. If Albert Einstein is in a box with no windows, there is no experiment that observer can do that can distinguish between these two events. And so Albert Einstein thought to himself, maybe there really isn't a difference between these two. Maybe they are, in fact, identical. Maybe these two are equivalent in some way. Let's think another way to think about this. That was the strong equivalence principle. This is more like a weak equivalence principle. Weightlessness, right? There is no way to distinguish between these two people who jump off a cliff in some sort of vacuum, air-free environment. What happens? They seem to be free-falling. They seem to have no forces exerting on them. They're just weightless. And they could play catch, right? They could throw a ball back and forth. And from the perspective of these two observers, that ball just moves straight back and forth between them. Obviously, if you're watching these guys from the side, then you're seeing the ball actually, with the people, accelerate downwards. But from the perspective of the observers who are falling, there's no downward motion. They just feel weightless. right? If they're in a box, if we had, let's draw a box around these people and move the air with them. Here's a box. And move the air with them. There's no test that they could do to determine whether they were actually in a box that were free falling downwards, or they were in a box that was floating away from all gravitational sources. Here is an example of people who are actually the same thing. These people are in the International Space Station. They are free falling around the Earth. They're basically in a pod that is taking their air with them and is falling towards the Earth. They just are moving fast enough that they never actually hit the Earth. But they could play this. They could play this exact game. They could stand on either side of the spaceship, and they could push a ball back and forth between them, and they would not feel any. They're feeling weightless. There's no gravitational force that they are experiencing within that rocket ship. Now, of course, that the astronauts and the balls and the spaceship and all of it are feeling a gravitational force, but they're all feeling it together. And there's no experiment they could do to distinguish where they are from one that was not free falling around the Earth, that was, say, way off in interstellar space, away from everything. So that is the starting point for Einstein's theory. And this leads to an interesting difference between Newton and Einstein. And that is that light behaves differently in these two scenarios. So for instance, I could conduct an experiment. Let's say I'm on the space shuttle and I'm here and I fire a laser in this direction. Well, I know that I'm in the space shuttle, and I know that in fact I am orbiting the Earth. And so, a short time later, I'm going to be moving, instead of in this direction, in this direction. I'm going to be moving in a slightly different direction as I orbit the Earth, right? But this is a way, if light isn't affected by gravity, that I could distinguish between being in orbit around the Earth within my space shuttle and being way off in a region that where there isn't any other masses around, right? Because what is that light beam going to do? Let's back up and think about what Newton predicts that light beam is going to do. Remember, according to Newton, the force of gravity is the gravitational constant G times the mass of the one object times the mass of the other object divided by their distance squared. And so this is what, according to Isaac Newton, is keeping the shuttle in orbit around the Earth. It is feeling this force, and that force is causing it to accelerate, and that acceleration is causing it to have this circular orbit. What about and everything that's in this rocket ship behaves the same way? The forces are different because these masses are different, but the accelerations are the same. What about light? Well, light is a massless particle. A photon has zero mass. So according to Newton, this m1 is zero, and so the force is zero, and so light should not be affected by gravity. So according to Newton, light should take this path and go straight, whereas the rocket ship should turn. But according to Einstein, not so fast. That is an experiment that this person could do on this rocket ship to distinguish between being in orbit around the Earth and not being in orbit around the Earth, right? All this person has to do is fire a laser in this direction, aim your laser exactly at this point, and if you're on a rocket ship in orbit around the Earth, that beam will seem to curve, right? Because at this point, it's actually missed this point that you were aimed at and has hit somewhere far over here instead. So, according to Einstein, that doesn't work. And according to Einstein, it must be that light is also bent by this gravitational field, even though Newton says that it would not. And so that's one of the major differences between Einstein's theory of general relativity and Newton's law of gravity, is that Einstein predicts that light should also be bent around as an object orbits another object, right? Light should also be affected by gravitational forces. So there has to be something else going on besides Newton if Einstein's going to be right. So what is Einstein's theory? Let's take a look. again, this is the Newton's theory of gravity on the left. On Einstein's theory is a curved space-time theory. What does that mean? Space-time is a four-dimensional substance that has three spatial dimensions, and time also as a fourth dimension. And the presence of matter bends that space-time. Here we have a representation. This is very difficult to visualize because it's very difficult to visualize a curvature in three-dimensional space. We're three-dimensional creatures. But we can visualize the curvature of a two-dimensional space. So let's make an assumption and a simplification and think about two-dimensional space. So the only directions are forward, backwards, and left and right. There is no up and down. And two-dimensional creatures on this two-dimensional in this two-dimensional universe, let's say they have the same sort of thing. Masses curve the space-time around them. They make it so that the geometry is not flat, right? And so light particles traveling through this region will follow the shortest path between 2 points, and that happens to be a curved path if you travel close to one of these massive objects that's bending and warping the space-time. Here's another way to visualize it. A rubber sheet analogy, again, for the two-dimensional equivalent of our universe. An ant traveling in a straight line will move like this. An ant moving in a straight line with a mass there, you can imagine this is a paperweight, and the paperweight is dragging that thing down, the sheet down. That ant will have a much longer path length to get to this point than to go straight through. And in fact, it's a shorter path length for this ant to move close to, but not exactly on the paperweight, to get to this point over here. And so this ant, which is representative of a photon, will take a curved path around this massive object instead of going in a straight line. And so that is one of the big differences between the gravitation according to Newton and the gravitation according to Einstein. And in fact, this is how the theory was first verified, right? It took about a decade after Einstein published his paper and made this prediction, and he did the calculations. This is a very hard thing to measure, right? Light is traveling very fast, and it is deflected very small amounts, even by very massive objects. And the first opportunity to really test this theory came from the sun. The sun is the most massive thing that's close to us. If we can measure the sun's effect on light as it passes by, then we can actually determine the difference between Newton and Einstein and see if Einstein was right. And this is very difficult to do because you have to observe a star whose light passes very close to the sun. And the sun is really bright. It's really hard to see stars that are right next to the solar disk. So they had to wait for a solar eclipse. And the next solar eclipse that happened was in the 1920s sometime. And they made an expedition, I think, to South America. And they waited, they set up all their equipment, and they finally were able to make an observation of a star that was right next to the disk of the sun while the sun was blocked out by the moon completely. And sure enough, that star was not exactly where they expected it to be. It was a little more than an arc second off from where it should be. And in fact, it was very close to the prediction that Einstein had made for exactly how far it should be off. And lo and behold, it turns out that light is affected by gravitational sources. And Einstein has a much more complete view of gravity than, in fact, Newton does. It's not that Newton was wrong, right? Again, it takes a very subtle measurement to be able to find a regime in which Newton's equation doesn't work. But Einstein's is a more complete theory. And this is a very good time for me to step back and talk about science in general. Some people often think that science, what's the point in science? Because we don't have a complete history understanding of the universe, and there's just going to be another theory that comes along that replaces it that's better. So what's the point of doing any of this? And we know that Einstein's theory isn't complete because it doesn't agree with some of the tenets of, for instance, quantum mechanics. So let me get on my soapbox for a minute and explain why this is important. It's not that Newton was wrong. Newton was correct. That formula works for almost every experiment that you could do. But there's a box around which you can draw and say Newton describes everything really well inside this box, right? And Einstein came along and said, aha, I think I can extend the box further out. Newton's theory and Einstein's theory are exactly equivalent inside that box. They have to be, because Newton's worked there, Einstein's must also work there. Einstein's theory is better because it pushes the bounds of that box outwards. It makes it so that it is applicable to a much larger range of astrophysical problems and physical problems. We know that there is a limit and an edge to the box that Einstein put forward. We have not yet done an experiment which fails Einstein's theory, but we know that there are experiments that can be done that will not work with Einstein's theory. We already know that it isn't very compatible with quantum mechanics. We haven't yet reached the edge of the box. We don't know specifically where it is, but it's kind of exciting because when we do reach the edge of that box, when we find an experiment that doesn't match with Einstein's theory, that's an opportunity to learn more about the universe. And maybe we can come up with another theory that, again, is just an improvement upon Einstein's theory that pushes that box out a little bit further. Whatever theory we come up with, we'll still have to agree with Einstein within the box that we presently have, because Einstein's theory works beautifully, perfectly within the box that we already have. Okay, I'll step off of my soapbox and get back to this curved space-time analogy, and we'll come back in the next video and talk more about it. See you then.